In this episode of Remote Calculus, we will be going over how to reason out antiderivatives when the chain rule is involved. This process is often given the name U substitution. Let's review a little bit about what we mean by antiderivatives though. And also, this notation, which is actually integral notation, does have some other deeper meaning behind it, but if you understand that deeper meaning, you see why this notation is often used when you are just trying to communicate that you're trying to find the general antiderivative. If you have used a lowercase letter for your function, it is also common to use an uppercase letter to represent the antiderivative of that function. So let's suppose we have a function f of x is the square root of 5x plus 2. Just a reminder about its derivative would be a negative 1/2 power, hence the square root is in the denominator. Notice I've left 5x squared plus 2 inside the square root. We multiplied by the original power, which was 1/2, and then the derivative of the inside is 10x. So the chain rule says when you're taking a derivative of a composed function, you take the derivative of the outside function, so 1/2 times the 5x squared plus 2 to the negative 1/2 power, and then the chain rule has us multiply by the derivative of the inside, the 10x. That simplifies down to 5x over the square root of 5x plus 2. Okay, so I was given a function, I found its derivative. The antiderivative of 5x over the square root of 5x squared plus 2 would then be the square root of 5x squared plus 2 plus some arbitrary constant. Because remember, the derivative of a constant is 0, so any constant could be added on here, and the derivative of this function is equal to what we have over here. So that's, again, just generally reviewing our mindset when we're finding antiderivatives. Here's another example. If I have cosine of pi x squared and I take the derivative of that, it would be negative sine of pi x squared, and then the chain rule says multiply by the derivative of the inside. I would then get 2 pi x as the derivative of the inside. So here's f of x, this is its derivative. Hence, the antiderivative of negative 2 pi x sine of pi x squared will be cosine of pi x squared, again plus an arbitrary constant. So once again, when you're finding an antiderivative, you are writing down the function whose derivative equals this. And that should always be your mindset. If you're finding antiderivatives, you really should always check your answer by taking the derivative of your answer, and it should equal the function you started with. So now let's get into U substitution. Okay, that was just kind of reviewing antiderivatives. So let's look at the two examples that we were just talking about, okay? I'm going to do the second example first. So we have the integral, or the antiderivative of negative 2 pi x sine of pi x squared dx. All of that notation means for us to find the general antiderivative. Notice I am going to rewrite it so that it's rewritten as negative 1 times sine of pi x squared, and then I am multiplying by the 2 pi x dx off on the right. I'm just organizing it so that things fit a little bit better. When you notice that you have an inside function, a composed function, you're going to simplify by calling that inside function some variable. U is very commonly used. So I'm going to take pi x squared, the inside function, and I'm going to call it U. Then you want to find its derivative, because remember, you have a derivative. You are trying to find the antiderivative. So if u is pi x squared, du is 2 pi x dx. Now I'm going to substitute so that my original problem has not been changed, but it's been simplified with this expression u. When I do this, there should no longer be x's at all in the expression. The only variable should be u. So negative sign of u is replacing negative sign of pi x squared, and then 2 times pi times x dx is what du is equal. So that gets replaced with du. Now I can look at that and I can say, oh hey, the antiderivative of negative sign is cosine. So I've completely simplified a messy function down to a simple expression. I easily can see what the antiderivative is. There's always going to be an arbitrary constant on the general antiderivative. I started off with x though and not u, so I replaced the u again with what it equaled in the first place, pi x squared, and there I have found the general antiderivative of negative 2 pi x sine of pi x squared. Looking at our first example, we have 5x over the square root of 5x squared plus 2, and I rewrote that as 5x squared plus 2 to the minus 1/2 power times 5x dx. The interior function, or the composed function, is 5x squared plus 2, and its derivative is 10x dx. So notice I have 5x dx, not 10x dx. So half, or 1/2 times du, or du divided by 2, will equal 5 times x dx. So when I go to replace things, I want to make sure that I haven't changed the original. So inside the minus 1/2 power is u, because u was 5x squared plus 2. And then the 5x dx is half of du, so it's getting replaced with half of du. I just have a simple power function now. So the power rule for antiderivatives is you add 1 to the power and divide by that new power. So the 1/2 is from this 1/2, and then I take my power, which was negative 1/2, I add 1. Negative 1/2 plus 1 is positive 1/2, so I'm dividing by that new power. Notice in this case, this 1/2 and that 1/2 divide out, and basically I have found the antiderivative of that power function. But I started off with x's and not u's, so I'm replacing u with 5x squared plus 2. And so the antiderivative of this is 5x squared plus 2 to the positive 1/2 power plus some arbitrary constant. Let us do some more examples. Here we have the antiderivative of secant squared of cosine of pi x times sine of pi x dx. So I have an interior function, cosine of pi x is plugged inside of secant squared. And in fact, pi x is plugged inside cosine, but we're going to focus on cosine of pi x being plugged into secant squared. If we call that u, then the derivative of u will be the derivative of cosine, negative sine, of pi x, but then the chain rule says the derivative of pi x is pi, so I multiply the derivative of cosine by pi. So du is negative sine of pi x, then times pi, and then dx, the rate of change of x. So now I'm going to try to replace things so that I still have the same function that I started with, but u is my variable instead of x. So I am trying to find the antiderivative of secant squared, and I've called cosine of pi x u, and then notice sine of pi x dx is what's left, and that's the opposite of du, so times negative du. So notice that secant squared, this is equal to that, and then -1 times du is equal to the rest of the expression. I now have a very simple form, secant squared. Secant squared is the derivative of tangent. So my antiderivative is -1 times tangent plus some arbitrary constant. But I started off with x's and not u's, and so I'm now going to replace the u with what u equals, which is cosine of pi x, and plus my arbitrary constant. That is my general antiderivative. We should always check our answers by taking the derivative, so to make myself feel better, I'll do the check by taking the derivative. So the derivative of tangent is secant squared, and remember, you leave the input alone. Then the chain rule says multiply by the derivative of the inside function, and this negative and that negative will divide or cancel out, or they'll multiply together to equal 1. So then I get secant squared of cosine of pi x times sine of pi x times pi, and that's exactly what we started with up here. So yay, we've correctly found the antiderivative. Looking at another example, here we have the antiderivative of 3 times sine to the 4th of 5x times cosine of 5x dx. This form comes up pretty often where you have sine or cosine raised to a power, and then that's being multiplied by the other one. Because remember, sine's derivative is cosine and cosine's derivative is negative sine. So when you see that combination, it's a perfect example of U substitution. So I'm going to let u be sine of 5x. It's the interior function because it's being raised to the 4th power. So the 4th power is the main function, and inside of it is sine of 5x. So the derivative of sine is cosine. So the derivative of sine of 5x is cosine of 5x times 5 due to the chain rule. So this time though, I don't have direct substitution. I'm going to have to identify how to adjust the du so that everything gets replaced exactly. The 3 can just get stuck out in front due to limit laws, the constant multiple limit law. I can factor the 3 out. And I have a 4th power, and inside of the 4th power is an expression I'm calling u, and du divided by 5 is equal to cosine of 5x dx. So the cosine of 5x dx is equal to du divided by 5. So the remaining part here I'm going to replace with du over 5. So I've taken that fairly messy expression and I've simplified it down to a simple power rule. So the 3 over 5 will be a constant multiple, and then when I find the antiderivative, I will have u to the 5th power divided by 5, and then there'll be a plus an arbitrary constant. So I have found the antiderivative of a 4th power by adding 1 and then dividing by that new power. I started off with x's though and not u, so I will have 3 over 25, 5 times 5, they're both in the denominator, is 25, and u was sine of 5x. And there we go. We have correctly found the general antiderivative of that function. Checking our answer. If I take the derivative of this, I get 3 over 25 times, whoops, I wrote a 4 instead of a 5 here. There we go. Now it's correct. So 5 times sine of 5x to the 4th power times cosine of 5x times 5, and then the arbitrary constant's derivative is 0. So these two 5's divide out the 25, and I'm left with 3 times sine of 5x to the 4th power times cosine of 5x. And that's exactly what we started with. All right, let's do one last example here. We have a ratio of x times e to the x squared plus 1 over e to the x squared plus 2x dx. So we're trying to find the antiderivative of that. You might want to step back a little bit and notice that that denominator is actually what we're going to treat as our main function. So e to the x squared plus 2x to the minus 1, we're going to kind of look at that as our main function. And then the x e to the x squared plus 1 dx is there due to the chain rule. So the interior function, the inside composed function, is e to the x squared plus 2x. Its derivative is e to the x squared times 2x. You're multiplying by that extra 2x due to the chain rule, and then the derivative of 2x is 2. So notice that that's matching this aside from being multiplied by 2. So if I divide du by 2, I will get x e to the x squared plus 2 divided by 2, so x e to the x squared plus 1. Okay, so anyway, we had a 2 here and we divided by 2, and then that 2 also got divided by 2. So du over 2 is equal to x e to the x squared plus 1, and that is the rest of the expression. So doing my substitution, I will have u to the minus 1 power, and then the rest of the expression is 1/2 du. So I took this fairly complicated expression and it's been simplified down quite a bit now. To actually find the correct antiderivative, it might be helpful to rewrite the minus 1 power in this form, and it might jump out at you. It's like, oh yeah, the derivative of ln is 1 over, so the antiderivative of 1 over u is natural log of u. So I found the general antiderivative, but I started with x's and not with u, so our last step is to replace u with what it equals, which is e to the x squared plus 2x, and then plus that arbitrary constant. Notice I have absolute value signs. Most of the time when you're dealing with these functions, what the domain of x's are going to make that expression of ln positive anyway, but technically ln's defined only for positive numbers, hence we put the absolute value signs to make the antiderivative correct. All right, well, that was a few examples using U substitution. The idea is you identify when you have an inside function, and if its derivative is the rest of the expression aside from a constant multiple, you can do this approach of U substitution. There are examples where you cannot do U substitution, so it's not the end-all be-all. There's another video that talks about when to U and when to not U, and it points out some examples where you cannot use U substitution. I also would like to point out that there's some cases that are technically U substitution cases, but you give yourself more of a headache to do U substitution than if you just thought about how you're trying to find an antiderivative. Take any time your inside function is just a linear function. If your inside function is just a linear function, then your antiderivative is just going to have you divide by that constant slope, and you don't necessarily need to write it all out as U substitution. Here, for example, The antiderivative of cosine is sine, and if I were taking the derivative of pi x, I would multiply by pi, but I am finding an antiderivative, so we will divide by pi. So if I take the derivative of this, its derivative will be cosine of pi x times pi, but that multiplication of pi will get divided by this pi, and I will have the function I started with. So this is the correct antiderivative. Notice I did not need to do U substitution.